Thank you very much, Esti. Indeed, I'll describe observations, but I'll also describe theory, astrophysics theory, which mathematicians may regard as close to observations, but we think of it as theory. And I wanted to start with this slide, since today is the evening of the Chinese New Year. And so on the left, you see a depiction of a goat. I mean, it does look like a goat. And that's the symbol for the New Year. On the right side, you see actually what nature produces, which looks pretty similar to that, except that it's on the scale of 100,000 light years. And what you see here is a jet ejected by a central black hole that we can't see, a tiny region of space that produces this huge jet stretching across the entire galaxy. And here in the middle, you see the dust lane of that galaxy. And so to celebrate the New Year, we might as well look on this side. And that will be the side that I'll focus on in this talk. So the topics that I'll discuss today are several. I'll start with imaging black hole silhouettes. The black hole itself is a dark region. It doesn't emit any light, but material around it emits light, and the black hole casts a shadow, and I'll discuss it. We have the technology, actually, to image that shadow. I'll then talk about pairs of black holes, black hole binaries. Just like with humans, when you put two black holes together, they form a binary system that is stable. If you put a third one, it's unstable, just like with humans again. And then I'll discuss the recoil of black holes as a result of either a merger of a binary or a triple system, three black holes kicking one of them at large speeds. Then I'll discuss the fate of stars near black holes. In particular, we wrote a couple of papers over the past few months with a postdoc, James Guillochon, about the possibility of accelerating stars like the sun close to the speed of light, which is quite remarkable if you think about it, near black holes, and near a pair of black holes. And the pair of black holes acts as a slingshot that ejects a star. If a star gets too close to a black hole, it can be disrupted by the tide that is raised on the star. Just like tides raised by the moon are observed in the oceans on Earth, when you get close to a black hole, the tide is so strong that a star can be ripped apart. And finally, I'll discuss the possibility that very small black holes may have been produced in the Big Bang. And in principle, they can account for the dark matter in the universe, whose nature we don't know. So the story starts 100 years ago, actually exactly 100 years ago. This is a special year during which there are lots of conferences celebrating the general theory of relativity. Einstein wrote the equations and published the first paper around November 1915. And a month later, Carl Schwarzschild found an analytic solution to the equations that Einstein did not appreciate. At that time, he was at the German front after he joined the military in Germany. And he sent a postcard to Einstein telling him that he found an analytic solution for a point mass. Einstein was thrilled to get this postcard and communicated its content to the Berlin Academy. And a year later, Carl Schwarzschild died at the German front. So the lesson from this story is that if you want to work out the full consequences of a theory for an extended period of time, you're better off being a pacifist. Because both of them were German Jews. The difference was that Einstein was a pacifist and Carl Schwarzschild was a patriot. So he volunteered to the German army. He was back then the director of the Potsdam Observatory. Nevertheless, he gave up on his academic pursuit, joined the army, and fought and found his death within a year. But he managed to find this solution. By the way, when I mentioned this joke in a colloquium I gave in Germany, there was not much laughter in the audience. And Schwarzschild solution is actually the full solution for a point mass in spherical symmetry. And it's characterized by a singularity, a physical singularity in the middle, meaning that if you were to make a black hole by collapsing a star or a cloud of gas, then the density of the matter will diverge at a given point in space. And at that point, Einstein's theory of general relativity breaks down. That's why we call it a singularity. That means that the theory is incomplete. And we know why it's incomplete, because on very small scales, you have to incorporate quantum mechanics. So we have the theory of quantum mechanics on the one hand, the theory of gravity on the other hand, and we would like to marry the two. Einstein himself tried to do that without success. These days, there are hundreds of, or maybe thousands of string theories attempting to do that. It's one of the frontiers in theoretical physics, but we don't have that theory as of yet. So at the moment, we don't really know what happens near the singularity of a black hole. It would be nice to know. One way to find out is to jump into one of these astrophysical black holes that I'm talking about. Problem is that once you get there, you won't be able to write a paper and publish it because the information cannot go out. A black hole is the ultimate prison. You can get in, you can check in, but you can never check out. And there is this horizon, the Schwarzschild horizon, at a distance of twice times Newton's constant times the mass of the black hole divided by the speed of light squared, inside of which there could be no communication to the outside world. What you see here as these lines are trajectories of photons, particles of light that have zero mass. If they are directed towards the black hole, they get absorbed. If they are directed from this point outwards, they may escape. And there is this photon orbit that for a Schwarzschild black hole, a non-spinning black hole, is 1.5 times the Schwarzschild radius, where a photon can execute a circular orbit. So in fact, at that radius, if you were to look straight, you might see your back, because photons coming from your back will reach your head. So a photon is gravitationally bound to a circular orbit at this radius. And you can see that, in principle, what an observer at infinity sees, if the observer is sitting on this side of the black hole, the observer will see a shadow cast by the black hole. So the question is, what happens to an observer close to the black hole? And that question was addressed in the movie Interstellar. And to address this question, Kip Thorne, in collaboration with a variety of people, imagined a camera located near a black hole and asked what will the camera see, taking into account the effects of the deflection of light, gravitational lensing, and time dilation, and so forth. And that's the image that they came up with for a black hole surrounded by a disk of gas that is emitting radiation that you can see in the movie. Frankly, I didn't enjoy much this movie because the science was not accurate, and the plot, other than that, was not particularly exciting. But this is the image produced, and in fact, it was just posted on the archive on AstroPH last week. So you can read more about it in this archive paper, how they produced it. In the past, scientists did not really worry about a camera next to a black hole because nobody wants to be close to a black hole. So in fact, we want to test the structure of space-time near a black hole to check whether Schwarzschild was right 100 years ago. And so one aspect of it is testing the general theory of relativity. The other one is testing the physics of gas accretion, the infall of gas into the black hole. Usually because of the strong gravity, the black hole sucks matter from the surrounding galaxy. And that's the matter we see. And so over the past 30 years or so, there were theories for how this matter behaves. In particular, if the matter is cold, it makes an accretion disk in which matter, just like near a faucet, matter is spiraling into the black hole by losing angular momentum through viscosity or viscous stress. And we would like to test these theories. By now, there are numerical simulations of that process. The second aspect, as I mentioned, is testing general relativity in the strong gravity limit. So the one important aspect of Schwarzschild solution is the existence of an event horizon, which is a one-way membrane. Matter can fall in but cannot go out. And if there was a hard surface, of course, matter impinging on the black hole would radiate much more energy. So we can easily test whether a black hole horizon exists if we could image the vicinity of the black hole. There were some papers recently talking about quantum effects that may show up in the context of, for example, firewalls, something like a surface, although it may be hidden just behind the horizon. So if there is anything pathological, anything unusual that may exist around the black hole, we would like to see it. There are, of course, paradoxes about black holes. For example, the information paradox. Matter falls in, carrying a lot of degrees of freedom, a lot of information, but the black hole itself can be characterized only by three numbers: its mass, its spin, the level of rotation that it has, and its charge. And in astrophysics, black holes do not have significant charges, because if it had a charge, opposite charges would immediately accrete onto it and cancel its charge, make it neutral. So we actually have only two numbers. And the question is, where does this information go? And of course, there is the process of Hawking evaporation, where radiation is emitted from the black hole, so perhaps that carries some of the information. But recent studies of that process say that no, it's actually not there. So this is an unresolved puzzle in fundamental physics, the information paradox. There is also the breakdown of general relativity at the singularity that I spoke about before. So clearly, black holes are good experimental laboratories for getting to study physics beyond the standard model that we have right now. So let's talk about the biggest black hole closest to us, which is a black hole at the center of the Milky Way galaxy, Sagittarius A star. We know that it's a black hole because we can monitor the orbits of stars close to it. Just like planets in the solar system tell us what the mass of the sun is, we can infer that the mass of the central object is about 4 million solar masses, 4 million times the mass of the sun. And it's very compact. The tightest orbit of a star around the black hole is as big as the solar system. And so within a scale of the solar system, we need to pack 4 million times the mass of the sun. There is no way of packing this with ordinary matter such that the matter would be stable and not collapse to a black hole. And so we are pretty confident, since we don't see that matter, and it looks like a dark object that is weighing a lot and it's extremely dense, that this is a black hole. Now, over the past 3 years, we haven't only seen stars orbiting the black hole. In one set of observations, there was actually evidence for a cloud, a gas cloud, approaching the vicinity of the black hole. This is an artist depiction, a simulation of the behavior of the gas cloud. In fact, this particular simulation in which the cloud is held by external pressure is ruled out because, as you can see from the date, when the cloud passes near the black hole, it was supposed to be disrupted, and it was not. Actually, it passed earlier this year or a few months ago. The cloud was discovered back in 2012, and you can see how it moves on the sky. It moves at a speed of a few thousand kilometers per second. And it has roughly the mass of 3 Earths and the size of the solar system, roughly. And you can see the trajectory of this cloud here in bracket gamma radiation. This is a particular line of hydrogen that allows us to trace the cloud relative to the background. There are various ways of making such a cloud. One is to have a star in the middle that we proposed with Ruth Murray Clay here at the Center for Astrophysics. Another one, which appears more plausible at the moment, is a model that we proposed with the postdoc James Gwillichon, where this cloud is one out of several P's on a bead. These are, you can imagine a stream of gas that fragments into clumps, and one of these clumps is passing near the black hole right now. There are more clumps along the way. And this stream of gas was produced by ripping out the outer envelope of a star. So there is a star which is not in the middle of the gas cloud. It's somewhere else, but it basically shed off a fraction of its envelope, and that's the stream of gas that is now clumping, and we see one of these gas clouds. And when I was asked by the New York Times about what the origin of this cloud might be, I was able to say something that made it to the quotation of the day back a year ago. I said that the experience is as exciting for astronomers as it is for parents taking the first photos of their infant eating. And the experience here is watching the black hole being spoon-fed by a star passing near it. So astronomers do like to watch this process going of spoon-feeding the black hole in real time. During our lifetime, we can see this cloud moving around the black hole and possibly feeding it. Now, the special thing about Sagittarius A star, this black hole at the center of the Milky Way, is that it's the largest on the sky. If we wanted to image the silhouette, you would like to look at the black hole that is the biggest on the sky. And this is Sagittarius A star. And one can imagine sending a technician, for example, this Verizon technician from a commercial a few years ago, that goes around and asks, can you hear me now? You can send that person to the vicinity of Sagittarius A star, and you can imagine what would happen as this person gets closer and closer. First, he encounters the innermost stable circular orbit, and that means that once he gets inside of it, he cannot move on a stable circular orbit around the black hole. That's at 3 times the Schwarzschild radius. Then he gets to the photon orbit, which is 1.5 times the Schwarzschild radius. Eventually, he gets to the Schwarzschild radius. Now, nothing would happen to his body at that point because the black hole is 4 million solar masses. The tidal force across a couple of meters, roughly the height of that person, the difference in force between his legs and his head, is not large. The overall acceleration is almost 1 million times the acceleration on the surface of the Earth. But it acts almost uniformly on the body of this person. So a person in free fall actually doesn't feel anything due to gravity. This was Einstein's insight that if you are in a free-falling elevator, you won't be able to tell that you are in a gravitational field. And so the only way to tell is if there is a difference in forces between your head and your toes. And that actually happens eventually. Within 10 minutes, this person, once it crosses the photon orbit, within 10 minutes it will reach the singularity and then be ripped apart. And of course, we would see from outside this person getting redder and redder with his voice getting sort of dilated. We will never see him crossing the horizon, but in his frame of reference, he would actually fall all the way to the singularity within 10 minutes. Black holes were called originally frozen stars because people thought of it, if you make a black hole from a star that is collapsing, at infinity, you see the matter only reaching the horizon. So it's sort of like a frozen image. And by the way, the same frozen image occurs in cosmology. Now it seems like the universe has a horizon, the de Sitter horizon. And when we look at galaxies as they exit from the de Sitter horizon in the future, their image will be frozen, just like in the context of a black hole. In fact, there are lots of similarities there. So one way to probe the space-time that is very effective is to put a clock around the black hole that is moving in orbit. And you might think, oh, how do I put a clock in orbit? I mean, if you don't want to risk a technician going there, you might do it remotely. We do have precise clocks in astronomy. In fact, almost as precise as the best atomic clocks. And these are called pulsars. These are neutron stars that emit a beam of radiation, and the emission direction is precessing around the spin axis of the neutron star. And you see it like a lighthouse. You see a beacon of light passing the telescope every so often, periodically. And by timing the arrival time of these pulses, you can measure time. And if there is a pulsar near Sagittarius A star, that would be fantastic. We could actually map space-time. So that we proposed back in 2004. And over the past decade, no pulsar was found in the vicinity of Sagittarius star, only except for last year, actually 2 years ago, 2013, there was a pulsar discovered serendipitously by chance. Unfortunately, this particular pulsar, which is very highly magnetized, it's called the magnetar, is located a fraction of a light year away. So it's not really very close to the black hole. And the search is on for finding pulsars close in. So imagine a hotspot, not a pulsar, a hotspot in the accretion disk moving around. You see it in the upper right panel. And that's the way the observer would see it. And here we are tilting the orbital plane as a function of time. And you see that the image of this hotspot looks quite different depending on the inclination angle. There is one side that appears brighter than the other side, and this is simply due to the Doppler effect. The beaming, as material is moving in the direction of the observer, it shines more brightly due to special relativity. There is also the effect of gravitational lensing. Photon trajectories are deflected by gravity, so you can get more than one image. And in fact, there are several images that one gets. You see it here in blue and green, depending on the orientation of the orbital plane relative to the observer. There is the primary image from the hotspot. And then there is a secondary image where the photons are moving around the black hole and are seen from a different direction. And finally, there is a third image, which is much fainter, where the photons execute a full circle around the black hole and come back on the other side. And altogether, one gets an image that looks like a crescent of the moon, for example. And you can see this crescent here. It depends, the exact shape of this crescent depends on the inclination of the orbital plane. So what you see in the top panel is a hotspot orbiting 30 degrees from the line of sight without any spin to the black hole. So that's what you would get. Here again, a non-rotating black hole, a Schwarzschild black hole with no spin, but at 10 degrees inclination. And at the bottom panel, you see a rapidly spinning black hole. And you can see that the crescent looks a bit different. Of course, in all of these crescents, there is a dark region due to the fact that when radiation is emitted behind the black hole, it gets absorbed. The black hole catches these photons, as I was mentioning before, and you get a silhouette, a dark shadow of the black hole. And this shadow is the signature of the event horizon. The scale of this shadow is of the order of 50 micro arc seconds. So if you are an amateur astronomer and you use a small telescope in your backyard, you can perhaps, under the best visibility conditions, reach a resolution, angular resolution of a few arc seconds. Here we are talking about a resolution which is a factor of 100,000 better. And obviously, even the biggest telescopes in the visible light, in optical band, cannot resolve such scales right now. However, there is a way of detecting it, as I'll mention in a few minutes. The spin of the black hole matters because the scale of the horizon depends on the spin. So here I plot the size of the horizon in Schwarzschild radius units as a function of this normalized or dimensionless spin parameter. So a maximally spinning black hole has a spin parameter of 1. A counter-rotating black hole spinning to the opposite direction has spin parameter of -1. This is a black hole spinning at the speed of light opposite to the direction of motion of a test particle. And you can see that the size of the horizon becomes roughly half the Schwarzschild radius, in fact, exactly half the Schwarzschild radius for maximally spinning black holes. Then there is the innermost stable circular orbit, which is abbreviated as ISCO. And that's the smallest radius for a circular orbit that is stable around the black hole. And for a counter-rotating orbit, this is 5 times the Schwarzschild radius. For a co-rotating test particle, it is the Schwarzschild. It is the Schwarzschild radius for a maximally rotating black hole, and it is roughly 3 Schwarzschild radii for low spin. Then there is the concept of the radiative efficiency. In principle, if matter can orbit on a circular orbit, it can release its binding energy in radiation. And the tighter the orbit is, the more radiation can come out. So the efficiency of converting rest mass into radiation depends on the radius of the ISCO, the innermost stable circular orbit. And for a spin parameter of unity, it can reach 42%. So in fact, you can think of black holes as very efficient engines that can convert up to 42% of the rest mass of material into radiation. That's the most efficient engines, except for engines based on annihilation of matter. For a non-spinning black hole, the efficiency is 5.7%. Now here you can see simulations of an accretion disk that has turbulence in it, which show the image that an observer at a large distance would see. And there is still this shadow and crescent shape in red here, but it also has some small-scale structure due to the turbulence. And there are lots of details in such simulations that we are not sure about. For example, how the radiation is produced. But roughly speaking, all of them show this crescent shape with a shadow in the middle. Now, why do we hope that to actually detect this shadow, to constrain it? Mother Nature was very kind to us. It's not always the case. There are problems in physics where you can work for decades, like the problem that string theorists are trying to tackle, and you are still not sure that you're on the right track. But in this case, Mother Nature was very kind to us. And because there are 3 fortunate coincidences. One of them is that the matter falling into Sagittarius A star is transparent to radiation with a wavelength shorter than 1 millimeter. And we are talking about radio waves emitted by the material. So Sagittarius A star was originally detected in the radio. At wavelengths shorter than 1 millimeter, the material falling into Sagittarius A star right now is transparent to the radiation, to synchrotron self-absorption, which is the dominant absorption process. And this is just now. If more material were to fall into Sagittarius A star in the future, it would be opaque. We wouldn't be able to see all the way through. Another coincidence that has nothing to do with the first one is that when you look at Sagittarius A star at radio wavelengths, there is intervening matter in our galaxy, which is blurring the image, scattering the radio waves. And it turns out that this blurring becomes insignificant, again, for wavelengths shorter than 1 millimeter. So we can actually see the image of this silhouette without being without the image being blurred by the interstellar medium of our galaxy. And finally, a third coincidence is that the scale of the horizon of Sagittarius A star and also the horizon of the black hole in a giant galaxy called the M87 that is much farther away from us can be resolved as long as you build a telescope with an aperture that has the diameter of the Earth for a wavelength of 1 millimeter. So in other words, the resolution of a telescope is the wavelength of the radiation divided by the size of the aperture. That you can read in any textbook on optics. So if you take the wavelength of 1 millimeter and ask how big should my telescope be in order for me to resolve the shadow of Sagittarius A star, you find that it has to be just the size of the Earth. Okay, that sounds ridiculous. How can you build a telescope as big as the Earth? But it is possible. In fact, there was a senior thesis back in the 60s that a student wrote with John Wheeler on imaging black holes, and the student concluded that it's not feasible, and then moved to work in on a different field. He is now a professor at UC Davis. And I actually contacted him, and I said to him that it was the wrong move, because we can actually do it now. But it's too late, I guess. And so these are images of the shadow of Sagittarius A star at different frequencies of radiation. The higher the frequency or the shorter the wavelength, the less blurring you get by the interstellar medium, and also the less absorption you get by the material next to the black hole, so you get sharper images. And the way to construct a telescope as big as the Earth is to have stations distributed around the Earth. And here you see the view of the Earth from the direction of Sagittarius A star. So if we were to sit on Sag A star and look at the Earth, this is what we would see. And you see here a number of millimeter observatories that can detect radiation at a wavelength of 1 millimeter. And if you were to measure not just the amplitude of the electromagnetic wave that arrives at these stations, but also the phase, you can correlate the arrival phase of the wave. And in principle, if you have a large enough number of stations, you can produce an image with a resolution on the scale of the black hole horizon. And in fact, this observational project is led by Shep Dolman, that is sitting somewhere in this audience over there with his son, is it? Yes. And the idea is to connect these observatories and correlate the signal that is detected at the different stations. So far, we have analyzed data from 3 stations that were correlated, and I'll talk about that in a minute. In principle, there is this concept of the Event Horizon Telescope, the full-fledged system of all these telescopes connected to each other, not just 3 of them. And to show you an example of what such an array of stations can do, here you see a simulated image of Sagittarius A star with lines indicating the polarization of the radiation coming from the material near the black hole. This study was led by Michael Johnson, a postdoc at the Center for Astrophysics. And you can see the polarization directions, and this is what the Event Horizon, the full Event Horizon Telescope would be able to produce, to reconstruct from the observations. And we will not only get a sense of how strong is the magnetic field near the black hole, but also its orientation. So that can be used to test theoretical models for how the gas behaves in the vicinity of the black hole. Right now, the Event Horizon Telescope is composed of these 3 stations. One is in Hawaii. It's called the Sub-Millimeter Array SMA, related or led by the Smithsonian Astrophysical Observatory of the Harvard Smithsonian Center for Astrophysics. And the second is JCMT nearby to that in Hawaii. And then another station is in California. It's called CARMA, the abbreviation for that. This is number 2. And number 3 is in Arizona. And these 3 form a triangle that can be used to set constraints. We can't get an image of the shadow, but we can set constraints on it. And in fact, in a paper that we published almost 5 years ago, we tried to fit the emission spectrum from Sagittarius A star and get the best fit model to the set of observational constraints that were available at that time. And we ended up with the conclusion that there is a probability distribution for spin parameters, and it's most likely a very low spin for this black hole. We got a probability distribution for the inclination angle and another orientation angle. So this is good. We get close to Sagittarius A star, but no cigar, in the sense that we don't have an image yet. There is another galaxy that I mentioned. It's called M87. It's a giant elliptical galaxy, sort of the type of galaxy that we will become, that the Milky Way will become once it merges with the Andromeda galaxy, its sister galaxy. And so the black hole inferred in the middle of M87 has a mass that is much larger than the mass of Sagittarius A star by some 3 orders of magnitude, almost a factor greater than 1,000, 1,400 times more massive than Sagittarius A star. But it's at a distance that is 2,000 times greater than the distance of Sagittarius A star, because this is a distant galaxy. But if you take the ratio of these 2 numbers, you get a number of order unity, meaning that we can, in principle, hope to image the shadow of this black hole. There is a big difference between M87 and the Milky Way, in the sense that there is a jet, just like the jet I had in my first slide, celebrating the Chinese New Year. This is the jet that you have in M87. And it's a very tightly collimated jet going all the way out. And usually theoretical models that produce a jet require the black hole to have a high spin. And so this black hole we know has a high spin, probably. And these are theoretical models of what the shadow around such a black hole might look like under different assumptions. That's a paper that we wrote with Avery Broderick when he was a postdoc in our theory group. And you can see that the image near this black hole depends also on what you assume about the base of the jet and how the emission takes place in the vicinity of the black hole. So you can get different images. It's not just dependent on the spin, but it does depend on the spin. And this is from a Nature paper led by Shep, published a couple of years ago, where the size of the emitting region was constrained to be smaller than the innermost stable circular orbit for a non-spinning black hole. So the conclusion from this paper was the black hole must have a spin, because we can see emission from a scale. The base of the jet is coming from a scale that is smaller than the ISCO for a non-spinning black hole. In fact, if you do a detailed analysis trying to fit the image, you get that the spin has to be pretty close to unity. The spin parameter has to be bigger than 0.9 or 0.96, depending on assumptions about the mass of the black hole. Now, obviously, if there is a black hole at the centers of galaxies, and almost every galaxy has a black hole at its center, when 2 such galaxies merge, you make a black hole pair. The Milky Way itself will merge within a few billion years with the Andromeda galaxy. We see this galaxy coming at us. The night sky will change. It will be a spectacular event to watch, actually, as the Andromeda galaxy is colliding with the Milky Way. But we see these events on the sky quite frequently. And here is an example where you see 2 cores of galaxies coming together. And there are many more such examples where you see 2 cores of galaxies coming together at different separations. So here the separation is close to 30,000 light years at the top left. And at the bottom right, the separation is less than 6,000 light years. And beyond that, below that separation, it's very difficult to separate with the resolution of these telescopes, separate the two cores. But we believe that such cores of galaxies spiral towards each other because of friction, gravitational friction, dynamical friction on the background matter, background stars and gas. And eventually, the black holes themselves get very close to each other after the stars surrounding them get stripped. And then eventually, they come together due to the emission of gravitational radiation. So here you see two black holes close to each other in X-rays. So this is a galaxy that has a lot of dust. You can't see much through the dust. But in X-rays, just like in the airport, you can actually image the center of this galaxy and tell that there are two centers of light. And here you see a double black hole system in the radio. And these black holes emit jets. So you can see two jets coming off. Here is another example. There are plenty of examples. This is the tightest black hole observed in the radio. The separation is around 20 light years. And the total mass is estimated of the two black holes is estimated to be about 1 billion times bigger than the mass of the sun. One way to tell that a binary exists is to look for periodic variation of the light. And I analyzed this signature about 5 years ago, where I argued that in principle you can find these binaries by looking for periodic modulation of the light. And if you ask what would be the characteristic period when, for example, gravitational radiation takes over and starts to be the dominant mechanism of bringing these two black holes together, compared, for example, to the friction on the surrounding gas, then you find that the period is convenient. It's about 7 years, comparable to the duration of a PhD thesis in our department. I'm not sure how long is a PhD thesis in math, but you can always imagine the two black holes coming even closer. Earlier, actually just a few weeks ago, there was a paper published in Nature arguing that perhaps there is evidence for such a system where the period is of order 5 years. The evidence is not very strong because they have observed this system only for about 8 years. But it's indicative, and more data is needed to figure out if indeed this is a system that gets to the point where gravitational radiation takes over and this binary black hole system will merge in less than the age of the universe due to the emission of gravitational waves. Now, you don't have to stop at two black holes. As I mentioned, even among humans, there are triple systems. That can happen, for example, if two black holes are in the process of coming together and then another galaxy comes in and joins the party. And then you can get 3 black hole systems. And we calculated in some papers with Girish Kulkarni and Lauren Hoffman the likelihood of getting such triple systems. And we figured that, in fact, these are unstable, and one of the black holes gets ejected with speeds that can exceed a few thousand kilometers per second. So in principle, such a speed would imply that the black hole crosses the diameter of the Earth in a few seconds. Okay, so these are very high speeds, and such black holes would escape from their host galaxy. So you can find these ejected black holes in the intergalactic medium.
These all have approximately the same mass?
No. In fact, the most common cases are ones in which you have the third body being less massive because, or two of them being less massive because there are many more of those than massive black holes. Here we see a pair of black holes coming together by the emission of gravitational radiation. And this problem was very challenging to solve numerically with computer codes until about 5 years ago, where a breakthrough was made. And right now it's there are codes that solve Einstein's equations in vacuum, except for 2 point masses orbiting each other, in full, and calculate the emission of gravitational waves. And that's what you saw here. Now, it turns out that when the two black holes come together, eventually they get to the ISCO, the innermost stable circular orbit, and then the small black hole plunges into the big black hole. So the gravitational waves are emitted in a preferred direction. And by conservation of momentum, there is a rocket effect. The remnant black hole that results from the merger of the two black holes gets kicked in the opposite direction. And what you saw on the right-hand side is that the kicked black hole, the recoiled black hole, could in principle escape from the host galaxy. And so these numerical simulations were able to calculate what is the recoil speed. And we incorporated that into galaxy merger simulations with my former student, Laura Blecka, and found that you could find recoiled black holes moving out of galaxies just due to the gravitational wave emission, the rocket effect from that. And then a question arose as to whether such systems are found on the sky. And the best candidate for such a system is shown here. These are two centers of light that represent two black holes, and they have a relative speed of about 1,000 kilometers per second and an offset of around 7,000 light years. Just a month ago, we posted on the archive an interesting suggestion for detecting gravitational waves. So these gravitational waves that are emitted by black hole pairs have very low frequencies. They have a characteristic, I mean, the two black holes, even at the ISCO, have an orbital time of order 1,000 seconds if they have the mass of Sagittarius A star. So we're talking about a wave period of order 1,000 seconds, or a wave frequency of 1 millihertz. And NASA, together with ESA, the European Space Agency, are promoting a concept to detect these waves in space. You can't do it on the ground because there is seismic noise, but you can, in principle, put laser beams separated apart that will measure the slight change in distances between the lasers as the gravitational wave is passing by. And that's the concept for a mission that is planned for launch 20 years from now, just measuring the change in distances using interferometry. This is called the ELISA mission. Now, we thought of something different. Just over the past year, the precision of atomic clocks improved dramatically by orders of magnitude. And so our suggestion was to use atomic clocks to detect gravitational waves. And the idea is as follows. There was a historic experiment that tested Einstein's theory of gravity done at Jefferson Lab, the building next to this one, where the physics department is. It was done by Pound and Rebka. So here you see one of them at the basement of Jefferson Lab, talking on the phone with his colleague at the top of Jefferson Lab, and measuring the frequency of gamma ray photons emitted by nuclei at the top of the building to be different due to the gravitational redshift, due to the fact that the gravitational field of the Earth changes the frequency of the photons. And using the Mossbauer effect, they were able to reach a very high precision that allowed them to see this tiny shift due to the Earth's gravity. So here is the Earth causing the gravitational shift. Now imagine moving the Earth under the experiment back and forth, tying it with a rope and pulling the Earth and then pushing it. Well, one way to do that is to put another Earth in a binary orbit. Then obviously what Pound and Rebka would find is a time-dependent time dilation effect, or time-dependent gravitational redshift effect that is changing periodically. This is a gravitational wave. So if you have a precise enough clock, then you should be able to detect gravitational waves. And the idea that we proposed was now with the precision of atomic clocks, that in particular optical lattice clocks, the technology of optical lattice clocks, one can reach a precision of order 10 to the minus 18, 1 part in a million trillion. So in other words, over the age of the universe, such a clock would not be off the exact time by more than a second over 10 billion years. And if you put such clocks in a triangular configuration, for example, around the orbit of the Earth, around the sun, and you shine laser beams that communicate the ticking rate of each clock, you would be able to tell that one, for example, if there is a passing gravitational wave and the two clocks are separated by half a wavelength, then you would be able to tell that they are ticking at different rates. Now, this is different from measuring changes in distances, the current design of ELISA, because you're basically measuring the change in the ticking rate or the frequency of the clocks relative to each other. You don't care about the fact that the distance changes. You just care about the fact that the clocks are not ticking. If they were synchronized to start with, you can record that they are ticking at different rates. At one half a wave period, at one time, one clock is faster than the other, and half a wave period later, it's the other way around, and this repeats periodically. So this is a different concept than interferometry for measuring distances. And
multiply the clock accuracy by the speed of light. How does that compare to the ELISA distance vector?
well, the issue of comparing it to interferometry is a subtle one, and we are looking at it now. But the point is that the precision of these clocks of 10 to the minus 18 in fractional time precision is comparable to the amplitude of the gravitational waves that you would get from a binary black hole system that has a mass similar to Sagittarius A star at a gigaparsec. Okay? In fact, such a binary system at a gigaparsec will have 10 times the amplitude. You can see it here. The amplitude is almost 10 to the minus 17 at a distance of gigaparsec, or 3 billion light years, for black holes with 1 million solar mass at a frequency of 1 millihertz, which actually corresponds to half a wavelength comparable to the orbital radius of the Earth around the sun. Okay, so that's a convenient coincidence that the orbital radius of the Earth around the sun is just corresponding to the type of frequency you get from a binary black hole system. And such a binary system, in fact, will coalesce within 10 wave periods. So if you catch it, it's very close to coalescing. And the wave period will change with time. There is this chirp that makes the period get shorter and shorter as the two black holes get closer and closer. So you can actually not only infer the mass of the system, but also the distance, because you have two equations. One telling you how the wave period or the wave frequency changes with time, and the other one telling you what the wave amplitude is. And you can constrain the mass and the distance from this. Now, when two black holes come together and one of them gets recoiled, that means that black hole can get ejected from the host galaxy. So there is actually an interesting prediction that one can make. The Milky Way galaxy was made out of building blocks. Early on in the universe, there were smaller galaxies, dwarf galaxies, that came together to make the Milky Way galaxy. So the earlier generations of galaxies were smaller than the present-day galaxies that we have. And so you can imagine that whenever two dwarf galaxies came together, the two black holes at their centers joined, and due to gravitational wave emission, the merger remnant got recoiled. Now, the gravitational potential of the host dwarf galaxy is relatively shallow, much shallower than that of the Milky Way. It corresponds to speeds of order 10 kilometers per second, whereas the Milky Way has a potential well of 200 kilometers per second. So the black holes typically get ejected with a speed of order a few hundred kilometers per second or less. And so such black holes would get expelled from the host dwarf galaxy, but they would still remain bound to the region that eventually makes the Milky Way. And so what you would end up with are floating black holes in the halo of the Milky Way galaxy. That's a prediction from this process. And there should be of order 100 such black holes. We analyzed it in a paper with my former graduate student, Ryan O'Leary. And they should carry very compact star clusters that were taken with them. So you can look for these compact star clusters. And we looked at a survey of the sky called the Sloan Digital Sky Survey and found some candidates for those that have to be looked at more carefully. Another interesting phenomenon that can take place is when you have two black holes with their star clusters due to the merger of two galaxies. It turns out that the two black holes tend to get into eccentric orbits. By scattering background stars, they tend to plunge towards each other. And when the secondary black hole, for example, gets very close to the primary black hole, the stars around that are tightly bound to the secondary black hole can get expelled. This is a slingshot effect. Imagine the two black holes acting as slingshots, and they eject the star gravitationally. Then you can end up with stars that are moving almost up to the speed of light. And together with James Bulletron, we calculated the statistics of such stars. And we found that there could be stars reaching almost the speed of light. So think about it. If you are occupying a planet next to such a star, this would be the journey of your life. The star would be ejected from the host galaxy, move through the universe, traverse it close to the speed of light, so you would be able to look at a vast volume of the universe. You would almost make the journey of a photon through the universe. And we are talking about real stars, the stars like the sun or more massive than that. But of course, the numbers of very fast stars is small. There are more stars moving less than the speed of light. We call them semi-relativistic hypervelocity stars. And we define them as new cosmological messengers, because if you look at the literature on studying the universe, the study of cosmology, people use primarily photons, particles of light. Okay? And here you have the opportunity to use material objects that move almost at the same speed as photons and bridge across cosmological distances. So these are new cosmological messengers. And if you ask how many of them are there within, let's say, a distance of 3 billion light years, or 1 gigaparsec, depends on the speed, but there could be 10 to the power 15 such stars moving at a speed that is about a tenth of the speed of light, but fewer of them moving at the speed close to the speed of light, of the order of a few thousand. Now, when such stars move across the universe, this is the metric describing our universe. As it turns out, our universe is very simple. Once again, nature was kind. We think we might know why, but not sure yet. Basically, geometry is flat. Okay, so the sum of angles in a triangle that you draw through the universe, and as you know, Riemann originally wanted to figure out if space is flat or not by drawing triangles. We now know that on the scale of the universe is flat. Okay, so you can describe it with and it's also expanding. So this is the metric of a flat spatial component of the metric, expanding with a scale factor that is changing with time. So the spatial scales are being stretched with time. And then there is the time component that is ticking at the same rate everywhere in the universe. And if you have material objects instead of photons that are emitted from a galaxy, then their velocity would be degraded or would be reduced as time goes on due to the expansion of the universe. The way to think of it is that in quantum mechanics, every particle has a de Broglie wavelength. And the de Broglie wavelength of a particle is just like the wavelength of light. It gets stretched by the expansion of the universe. And so for a massive particle, it could be a star or anything, The de Broglie wavelength scales like 1 over the momentum or 1 over the velocity, and it's being stretched like the scale factor, so therefore the velocity is reduced inversely with a scale factor. And that's in difference from photons, where the velocity, the speed of light is constant. So you get a different relation between distance and travel time than you get for photons. And you get a change also in the brightness of the star due to relativistic beaming. And a star could get deflected by an intervening galaxy due to the gravitational effect of that galaxy. The effect is similar to gravitational lensing. And so we calculated those effects, and you can find them in our paper. If the star gets too close to the black hole, then it can get ripped apart by the tide, as I mentioned. And such events occur once per 100,000 years for galaxies that have a single black hole. But the rate can be enhanced by almost a factor of 1,000 for black hole pairs. And black holes that are too massive, like more than 100 million times the mass of the sun, they would swallow the star whole. They would not rip it apart because the gravitational tide would be too weak. But black holes that are less massive than 100 million would rip apart a star like the sun. And the feeding rate of the black hole would be huge, and it could lead to outflows. So here you see a simulation that was made by my collaborator, Kimi Hayasaki, with my former student, Nick Stone, where you see a star being shredded into a spaghetti-like stream of gas. This is called spaghettization of the star. And you can see this stream going around the black hole. In this case, the black hole has a spin, and it's counter-rotating. It's with a spin of minus 0.9 when the chance of the stream intersecting itself is actually larger than if the stream was prograde, moving in the same direction as the spin of the black hole. And so you see the stream intersecting the stream of gas. This is the XY projection. This is the YZ projection of the same process. And eventually, the material intersects itself and makes an accretion disk around the black hole. Now, this is the case where the gas is cooling very efficiently, so the stream becomes very thin in the simulation. This simulation was completed. I mean, the paper was posted just last month. And it represents state-of-the-art calculations of this process. If you allow the gas to cool very efficiently, the situation is quite different. You can see here that the stream becomes very thick because it heats up due to the stream-stream collisions. And then you make a torus of gas that is rather thick around the black hole much more quickly. The tidal disruption rate could be enhanced if the black hole has a recoil. For example, when two black holes come together, there would be gravitational wave emission. And after that, the black hole will be kicked. And then it will see fresh material that it can eat along the line of sight. So it can actually capture stars along the path of the recoil and produce many more tidal disruption events. We found with Nick Stone, we found that roughly every 100 years, in such a case, you can get a disruption of a star. So there is a chance that a PhD student would see two such events coming from the same galaxy. And in fact, a couple of years ago, there was actually more than that, 3.5 years ago, there was one tidal disruption event of a star observed at a cosmological distance that likely produced a jet pointed at the observer. And we can see such a jet, because it's so bright, all the way to the edge of the universe. And an interesting question about the jet is whether the jet will be aligned with the spin of the black hole, or whether it will be aligned with the orbital plane, perpendicular to the orbital plane of the debris from the disruption of the star. Because the debris from the disruption of the star has no knowledge of the spin axis of the black hole. So in principle, it can be aligned at an arbitrary angle. And then the question is, where will the jet go? Will it be aligned with the angular momentum vector of the orbit of the original star, or with the spin of the black hole? Turns out that since this system with a jet was seen steadily for 2 weeks without changing in brightness, we can rule out the possibility that there is precession of a jet around the black hole spin axis. And the most likely situation is that, in fact, the jet was aligned with the black hole spin. So that's the conclusion we drew from that. Now let me get to my final topic, which is primordial black holes produced in the Big Bang. And in principle, if you imagine the universe at early times, it was seeded with density perturbations, inhomogeneities. And if you have a density enhancement of all the unity across the scale of the horizon of the universe itself, the horizon of the universe will collapse to make a black hole. But since the horizon is very small at early cosmic times, you would make a tiny, microscopic black hole with a microscopic mass. So this could be, for example, the dark matter. You could have some rare perturbations that made up the dark matter, because we won't be able to tell. Now, Hawking evaporation would eliminate all the black holes with masses less than an asteroid mass. But black holes with masses more than 10 to the 15 grams, more than the size of an asteroid, the mass of an asteroid, have an evaporation time that is longer than the age of the universe. So they should still be around if they existed. And interestingly enough, such a black hole that has an asteroid mass has the size, the Schwarzschild radius of the size of a proton, 10 to the minus 13 centimeters. So if such a black hole passes through a proton, it will disintegrate the proton into quarks just due to gravity. That's quite remarkable. So just like I was talking before about destroying stars, here we are talking about destroying a proton with a black hole, passing through it due to the gravitational tide. And a surgical passage of such low-mass primordial black holes through the Earth is difficult to detect because the only thing it does is excite seismic waves. So the question is the dark matter made of such black holes? Could it be primordial black holes? And we wrote a couple of papers with a postdoc that worked with me, Paolo Pani, where we ruled out the possibility that the dark matter is made of such black holes. And the first part of the argument had to do with black holes with a mass between the mass of the moon and the mass of the sun. Okay? And it turns out that if you take a black hole and surround it with a mirror, and this was argued back in the 70s, you take a black hole, put a mirror around it, a reflecting mirror, and let radiation bounce back and forth. If the black hole has spin, it turns out that the spin energy of the black hole can be converted into low-frequency electromagnetic radiation with a wavelength comparable, or with a frequency comparable or lower than the spin frequency of the black hole. And you get a black hole bomb, because the black hole radiates these waves. They bounce off the mirror, come back. Just like in a laser, they bounce back and forth between the mirror and the black hole, and they get amplified every time. And so you build up an energy density inside this cavity, spherical cavity, such that eventually you'll get an explosion. All you need to do is surround a black hole with mirrors. So is that at all just an academic exercise? Well, for decades people thought, but then it occurred to me that, in fact, in the early universe, if you look at these primordial black holes, they were surrounded by a mirror. It's called plasma, or ionized gas. And it turns out that when you write the dispersion relation for a photon in an ionized gas, in a plasma, you can think of it as a massive particle. The frequency squared is equal to the plasma frequency squared plus the wave number squared times the speed of light squared. That's similar to having the energy squared of a massive particle equal to its mass squared times the speed of light to the fourth plus its momentum squared times the speed of light squared. So in fact, it's as if the photon acquires a mass. And if you think about it, how does a mirror operate? When you look at a mirror, you see your reflection. The reason you see a reflection is because the plasma frequency inside the metal, there is a silver coating to the mirror, to the back side of the glass, which is basically a metal that has free electrons in it, electrons that are free to move, and it has some characteristic plasma frequency. related to the density of these free electrons. And you're looking at light where the frequency is smaller than the plasma frequency, and therefore the light gets reflected. That's what a mirror is. So if you look at these primordial black holes, and they are surrounded by a dense enough plasma in the early universe, they will act, the plasma will act as a mirror. And you can extract the spin energy of these primordial black holes. It's very difficult to imagine them being formed without any spin. They would likely be formed with spin. And you can extract this energy. And now, as the time goes on, this mirror will eventually disappear because the universe is expanding and the plasma frequency will go down, the density of matter will go down. And so you will end up with the energy that was stored inside this cavity being dissipated into the radiation field in the universe. And so you can end up with the energy distorting the cosmic microwave background. And we have limits on that. So by using those limits, you can actually rule out the possibility, this is the fraction of the dark matter that is in the form of primordial black holes as a function of their mass. And this mass is roughly the mass of the moon here, all the way up to the mass of the sun. We can rule out the possibility that primordial black holes with even a little bit of spin are the dark matter, based on the fact that we haven't seen energy injection into the cosmic microwave background during the later history of the universe. So that's one argument. Then for lower mass black holes that have a mass of the order of an asteroid mass, less than the mass of the moon, you can rule them out by considering neutron stars. So if such a black hole passes through a neutron star, a very dense star, then it turns out that it will excite modes inside the star and eventually get trapped and sink to the center of the neutron star and start eating up the neutron star. So turns out, if you do the calculation, and that's a very detailed calculation, that the existence of neutron stars in the centers of galaxies where there is a lot of dark matter rules out the possibility that the dark matter is made of primordial black holes with masses between the mass of an asteroid and the mass of the moon. And once again, the limits are quite significant. So let me summarize the punchline of my talk. And in the first part, I talked about the Event Horizon Telescope, a very exciting frontier that many of us are involved in. And in fact, we are now collaborating with Andy Strominger from the physics department, with Peter Gallison that was here, and with S.T. Yao on this project, together with a number of astronomers. And the goal is to image the silhouette of the black hole at the center of the Milky Way galaxy and in M87, and constrain general relativity or deviations from general relativity observationally. And then I mentioned the existence of pairs of black holes, black hole binaries, that can be looked for in electromagnetic radiation. They can also accelerate stars close to the speed of light, which is quite remarkable, acting as slingshots. And when they coalesce, they get recoiled. And so you can look for offset black holes from the center of galaxies, and also for floating star clusters in the Milky Way galaxy. And finally, primordial black holes probably do not make up the dark matter in the universe. Thank you. And I'll be glad to answer questions, especially from the students in Andy's class 211R, black holes from A to Z.
Well, I'm not a student in the class.
Okay, go ahead.
Could you just say a few words about the origin of the submillimeter wavelength radiation that's supposed to see at the HV?
So the question was, what is the source of the radiation that we see coming from Sagittarius A star? This radiation is thought to be emitted by electrons, relativistic electrons, gyrating